So, good morning friends. In the last lecture, we have solved the problem based on the KP and KC and Q. We said that if Q is greater than KC, then the backward reaction is possible. Means more number of reactant molecules will be again reformed. If Q is equal to K, in that case the forward as well as backward reaction will be in the equal concentration. If Q is less than Kc, then the forward reaction is possible, more number of product molecule will be formed. Today we will see the relation between, as I told you, that relation between Kp and Kc. Kp and Kc. We know that what is the Kp and what is the Kc. Kc, when we use the concentration term, then it is the Kc, and when we use the pressurized term in the gaseous reactant molecules, in that case Kp is used, partial pressure of the gases are used, in that case the Kp is used. So let's try to understand the relation between Kp and Kc. We know we always take the famous reaction, A number of gaseous molecule plus B number of B gaseous molecules. Again it is the equilibrium reaction. We will form the C number of C gas molecule plus D number of D gas molecule for the irreversible reaction. Now Kc for this reaction we can easily write Kc is equal to, we are all of us have learned how to write the Kc value, that is product concentration raised in the proper powers divided by the product of concentration of reactants raised in the proper powers B raised to B. Right, this is the Kc terminology we use, where the concentration of the species are taken dimensionless by dividing the respective concentration expressed in the moles per liter. Moles per liter will become the dimensionless quantity. Now if this A and B terms are C and D terms, those are the products and those are the reactants. If we express in the moles per liter, that is concentration, moles per liter, that is concentration, then Kc is used. Now since we have written here it is the gas molecule, we know the ideal gas equation. Let's assume these reactant as well as product gas molecules behave ideally. We know that the ideal gas equation Pv is equal to nRT, right? Then this P, pressure P is equal to nRT divided by phi. That can be written as n divided by phi into RT, where pressure is in the unit of the pressure is bar, unit of n is number of moles, it is the number, unit of volume is in liter, unit of R, that is molar gas constant, is mole per degree Kelvin per liter, and T is the temperature, that is having the unit K, that is degree K, right? Now if you substitute this P value, that is n divided by V into RT in this equation, let's consider this is as a equation number 1. Then what equation 1 becomes? Equation 1 becomes how it becomes? Kc is equal to C raised to C, that instead of writing the concentration here, we are using the partial pressure of this gas molecule, reactant as well as product gas molecule. So Kc becomes, according to this equation, Pc, that is partial pressure of C gas molecule, that is product molecule, raised to the power Pc raised to the power C raised to the, Pc is what? Partial pressure divided by RT. Pc divided by RT. Next is pressure of D, partial pressure of D divided by RT raised to the power D divided by partial pressure of A divided by RT raised to the power A, partial pressure of B divided by RT raised to the power B. What? We have replaced the concentration term as a pressure term, right? So we have put this equation, that is N divided by V, that is the concentration, divided by RT. That this term we have converted into the either partial pressure. Now, therefore, where partial pressure of species are made, in this equation, the partial pressure of this species are made dimensionless by dividing the respective pressure by 1 bar in this equation, 1 bar. Therefore, the next equation comes, that is Kc is equal to what? Pc, that is 1 bar pressure divided by 1 bar pressure, Pc concentration raised to C, Pd concentration raised to D, and Pa concentration raised to A, and Pb concentration raised to B. This comes out to be what it comes out to be. It is 1 divided by RT, that equation we are rearranging again this equation, 1 divided by RT raised to the power C plus D, because if we divide by 1 bar, this Pc will become 1 and this Pd will become 1. Therefore 1 divided by RT, 1 divided by RT. Therefore again this 1 divided by RT, this equation becomes 1 divided by RT, that is A plus B. Therefore I will write again Kc is equal to what? Kc is equal to Kp raised to Kp into RT raised to the power A plus B minus C plus D. See, this Kp is written while converging this term. I have taken this RT as a upper side, 1 over RT, right? Therefore, the Kc is equal to Kp into RT raised to minus delta N. This A plus B is what? A plus B is number of moles, right? Number of moles. Therefore this Kp I can take this side and Kc I can take this side. That comes out to be Kp is equal to Kc, I can change the sign, that is RT raised to the power delta N. Now this delta N becomes the number of moles of product minus number of moles of reactant. In this case it was number of moles of reactant minus number of moles of product. This Kp I have taken this side and this Kc I have taken this side, and while I have changed the sign of this delta N. That is according to the rules of the mathematics, right? Now this RT can be made the dimensionless quantity, that is Kp is equal to, this RT value can be made dimensionless quantity by Kp and Kc are the dimensionless. We know that Kp and Kc are dimensionless. This RT value can be made by dimensionless, that is equal to 0.0831 per degree Kelvin T raised to delta N. That R value I have converted into the dimensionless. Therefore Kp becomes Kc, Kp becomes Kc into 0.0831 per degree Kelvin into T raised to delta N. Delta N, it is the number of moles of the product minus number of moles of the reactant. Therefore, this is the very important equation while solving the problems. That is Kp is equal to Kc into 0.0831 raised to the power minus 0.0831 per degree Kelvin into T raised to the power delta N. This is the relation between Kp and Kc. What we have done, we have converted this Kc equation into the partial pressure equation, that is, we have taken this ideal gas equation, we have taken this A and B, C and D are the ideal gas molecules, then P is equal to N divided by V RT, that is P is equal to CRT. What is this? N divided by V? N divided by V, it is the number of mole divided by volume. Yesterday we have calculated while solving the problem. That is concentration term. This concentration term can be written in case of the partial pressure. Concentration term can be written in the partial pressure. Therefore, concentration in this equation C is equal to what? P divided by RT. Right? P divided by RT. This C, that is the concentration in this equation. C concentration, D concentration, A concentration, B concentration, that we have replaced by this P divided by RT in this equation. P divided by RT in this equation. PC divided by RT, that is partial pressure of C divided by RT, partial pressure of D divided by RT. Right? Then what we have done? We have made this partial pressure PC or PD or PA or PB by dividing this partial pressure by 1 bar. That is partial bar. The partial pressure made dimensionless, since pressure it is in the bar. If you divide it by 1 bar, partial pressure already is in the bar. This partial pressure is already in the bar. If I divide it by 1 bar, that comes out to be dimensionless. Right? That comes out to be dimensionless. That is 1 divided by RT. C plus D, that is according to the rule of mathematics, and 1 divided by RT, A plus B, that we have replaced. Here what we have done? We have done this 1 divided by RT, 1 divided by RT, this terminology we have converted here, A plus B minus C plus D, where this Kp term comes out to be, while taking the inverse of this RT. Here we have written the RT. Therefore, remaining things we can understand very well. So, the relation between Kp is equal to Kc into 0.0831 per degree Kelvin T raised to delta N. Here, this 0.0831. See, this Kp is dimensionless, Kc is dimensionless. T is also dimensionless. What is the only temperature? Degree centigrade. It was the R only, that was the dimension quantity. That R, molar gas constant value, that we have converted only simply 0.0831. That we know that R values are expressed in the different unit. That is molar gas constant values are expressed in the different unit, that is made dimensionless. 0.0831 per degree Kelvin, that is molar gas constant value. It is the dimensionless value, right? There are other ways of the expressing this R value, but in this case we are expressing as 0.0831 per degree Kelvin. Remember this equation, right? Now, what we will next learn is that the molecular interpretation of equilibrium constant. Molecular interpretation of equilibrium constant. molecular interpretation of equilibrium constant, right? We know that equilibrium constant indicates the specific composition of the reaction mixture. When you write the equilibrium constant Kc or Kp or K, it indicates that. What it indicates that? It indicates the specific composition of mixture when the reaction has attained the equilibrium, and it is the function only temperature. But it is the only temperature dependent. For a particular reaction, it is forward direction or backward direction. It has the Kp or Kc. This Kp or Kc changes. This Kp or Kc changes with respect to only the temperature. At given temperature, it is the constant value, right? So, significance of equilibrium constant, that lies in the significance of the equilibrium constant, which changes with the temperature. Now, one can consider the Boltzmann distribution. What one can consider the Boltzmann distribution? Molecules of reactant and the product over their available states of the energy level at the equilibrium. What it indicate that? What it means that the reaction, if you take as A plus A, that is giving the B that is giving the A. Suppose the reversible reaction. If this reaction is exothermic one, exothermic reaction. If the reaction it is exothermic one, then what is the Boltzmann distribution? What is the Boltzmann distribution? I will show you the Boltzmann distribution. The Boltzmann distribution will be like this. I hope you can see this Boltzmann distribution for this reaction. What I have said. What we are learning? We are learning the molecular interpretation of equilibrium constant. What is happening at the molecular level, that we are learning? Molecular interpretation we are learning. So if we consider this reaction A that gives the B, and this reaction is exothermic. What is the exothermic reaction? The reaction in which heat is evolved, and the product which is having lower in energy than the reactant, therefore it is favorable to the more product side. Since the product is having lower in energy than that of the reactant. Why? Because during the reaction the energy is liberated. That is called as the exothermic reaction. During the reaction, if the energy is absorbed, then that is called as the endothermic reaction. We know that. So, what terminology I have next used? It is the Boltzmann distribution. Boltzmann distribution. So, what is the Boltzmann distribution? So, if I take a container, in which suppose any gas molecule is present, suppose hydrogen gas molecule is present. Suppose this concentration of this hydrogen gas molecule in this container is 2 mole. The number of moles of hydrogen gas molecules are 2 molar. Now, we are talking about the Boltzmann distribution. Remember that some of the gas molecules will have the higher energy than that of the average number of gas molecule, and some of the gas molecule will have the lower energy than the average energy of the gas molecule, and many of the gas molecule will have the average kinetic energy. Remember that. Kinetic energy, according to kinetic energy of the gases, we have learned in the 12th standard, the gas molecule inside the container will have the kinetic energy, right? All the gas molecules inside the container will have the kinetic energy, because all these gas molecules are always in the random motion, right? Always in the random motion, therefore they are having the kinetic energy. Now, in that kinetic energy, most of the molecules will have the average kinetic energy, but some of the molecule will have the higher kinetic energy than the average kinetic energy, and some of the molecule will have the lower kinetic energy than the average kinetic energy. That is what? That is the function of temperature. This average kinetic energy is the function of temperature. If we increase the temperature, the kinetic energy of the gas molecule will also increase, right? If we decrease the temperature, the kinetic energy of the gas molecule will also decrease. That energy levels of the gas molecule, some of them will have, most of the molecule will have the average kinetic energy, some of the molecule will have the higher kinetic energy, some of the molecule will have the lower kinetic energy, but many of the molecule will have the average kinetic energy. This distribution of energy levels, that is called like the Boltzmann distribution. Remember. Now, if we consider, come to the point, if we consider this A and B as a gas molecule, A is converting into the product B, and this reaction is exothermic, and these are the energy levels of A gas molecule, that is reactant molecule. These are the energy levels of reactant gas molecules, and these are the energy levels of product gas molecule, B gas molecule, right? This is the Boltzmann distribution, that is the energy level coming on down, decreasing, that is only gas. So these are the population is what? Number of gas molecules, those are having average kinetic energy in that population, that is the level of population we can call, and less number of molecules will have the higher kinetic energy than the average kinetic energy. That number of gas molecules are present in that energy level, that is called as the population, and this is the energy, right? Now, this B energy levels, those are having lower in energy, this much amount. This lower in energy, this B energy level, 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 those are having lower in energy by this much amount, delta amount, right? So the B gas molecules will have the lower in energy than the A gas molecule, right? In that case, more products are favored. The difference in the energy level between the gas molecule is little bit more. The gas molecule as well as product molecule is very more, little bit more, not very more, very much, little bit more, right? So in this case, since it is the exothermic reaction, more number of product molecule will be formed. Therefore, reaction will be shifted to the product side, that is B side. The reaction will be shifted to the product side, right? Less number of reactant molecule will be formed. So what will happen in the next step? If I take the graph of, wait for a moment. So what is happening in this case? This is what? The densities of energy level is much more greater than B. The density of the energy level is much more greater than B. I forgot to change the diagram. Sorry. Wait for a moment. I will show you the graph. Only 1 second. I hope you will wait for the half a minute. I hope you are understanding my language. As I told you that we will be completing the syllabus before our exam. So Forget it, it is not getting copied, so I will copy directly. So let's consider now this diagram. So consider this diagram. The previous diagram was this, right? The energy level that we have seen. Now concentrate on this diagram, below diagram. The diagram. Just concentrate on this diagram below side diagram. So according to the equation, what equation? We have learned the equation, that is delta G0 is equal to minus RT ln K. That final equation that we have learned, right? So in this equation, K contains the delta G, right? Hence it is obvious that entropy also plays the important role. Remember that I have used the terminology entropy. Entropy is what? Entropy is the measure of disorder, right, in this reaction. So when the energy levels of a gas molecules, they are very much little bit less, much less the gas molecule. What is the energy level? These are the Boltzmann distribution. What is the Boltzmann distribution? It is the energy level present in that molecule, right? When the energy levels in a gas molecule for this reaction, that is A is converting into the product B, right? So energy levels play the important role. Therefore entropy also plays the important role. If the distribution of energy level is very less, there are more number of energy levels, so it decides the composition of the reaction mixture equilibrium along with the Gibbs free energy. This is clear that even though energy level for the species A is higher than that of the B, they are more closely spaced than that of the B. Right, in this equation they are more closely spaced. This B energy levels are higher in the space, more space, and this A energy levels are less in space, less number of space. The population will be therefore more than that of the B and will dominate the equilibrium. Why? The population, number of population in the A energy level is very high. So the number of population energy level is high. The number of energy level, the number of different energy levels are present in the A. So entropy plays the important role, right? We have learned this equation, delta G0 is equal to minus RT ln K, right? Therefore the entropy will dominate the equation. So I will rearrange this equation, that is ln K is equal to minus delta G0 divided by RT. Delta G0 divided by RT. What I have written? ln K is equal to delta G0 divided by RT. Right? Minus delta G0 divided by RT. Minus sign taken this side. Right? I simply multiply by minus sign. So we know the equation. In previous chapter we have seen the equation. That is what? That is delta G0 is equal to delta H0 minus T delta H0. As why we have introduced this entropy term. Why entropy term? The distribution of the energy levels is very high. The spacing between the two different kind of energy level is very high in case of the A. Right? Although B is having lower in energy. Although B is having lower in energy, the reaction mixture, what? Number of products as well as reactants are there, but the A energy level is very high. In that case, entropy predominates. Entropy plays the important role. If I substitute this delta G0, this delta G0, suppose this is the equation number 2 and this is the equation number 1 and this is the equation number 3. If I put equation 3 in 2, put 3 in 2, equation 3, that is delta G0. I will put there this equation, delta G0, instead of delta G0 I will write delta H0 minus T delta S. That comes out to be, this is the negative sign, this is the negative sign, there is the negative sign. That comes out to be ln K is equal to minus delta H0 divided by RT plus delta S0 divided by R. How it comes? Since I will write again here, ln K is equal to, instead of delta G0 what we are writing, minus delta H0 minus, this minus will become plus T delta H0 divided by RT. RT is for both the side, right? RT is for both the side. Therefore, it comes out to be ln K is equal to what? Minus delta H0 divided by RT plus T delta H0 divided by RT, because this RT is for the both sides. This TT will get cancelled. Therefore, ln K is equal to minus delta H0 divided by RT plus delta H0 divided by R. Right? So that's what I have written here. Suppose consider this is equation number 4. Then if I remove the ln K in this equation, but it comes out to be K is equal to e raised to minus delta H0 divided by RT into, because according to rules of exponential, e raised to delta S0 divided by R, delta H0 divided by R. So this is the equation, final equation number 5. So for the exothermic reaction, delta H0 is negative. If exothermic reaction, delta H0 is negative, that is standard enthalpy of formation is negative, hence K will be the higher value. If this delta H0 is negative for exothermic reaction, heat is evolved in the reaction. The product molecule, those will have the lower in energy, right? In endothermic reaction, the product molecule will have the higher in energy, in which the heat is absorbed. So for the exothermic reaction, delta H0 is negative, hence K will have the higher, and it can be expected to have the equilibrium constant favor the product formation, more number of product formation, right? In spite of exothermic character, the entropy of the reaction delta S is positive for endothermic reaction. For endothermic reaction, delta S is positive, more positive, and this is least negative. The ln K value will be lower. If we consider the reaction A and B. For the endothermic reaction, the reaction will go to this side, more number of reactant molecule will be formed, right? For the endothermic reaction, that is the difference between exothermic and endothermic reaction. When it happens, the distribution of the energy level, A is very less. As of now, this is enough for the today. Next lecture we will see the response of equilibria to the conditions, right? Enjoy the lockdown. Bye bye.